In this video, we are going to take a look at what the definition of a limit of a sequence is, as well as a lot of properties for how we can find limits of sequences. So if the terms of a sequence approach a unique number L as n increases, then we say the limit as n goes to infinity of a sub n equals L. And it exists, the limit exists, and therefore the sequence converges to L. So when we're talking about convergence of a sequence, it's going to be, does the limit exist when we take this infinite limit? If the terms do not approach that single number, then the sequence has no limit and the sequence diverges. What these look like ultimately is exactly what the limits at infinity looked like for functions. When talking about limits of functions going to infinity, it would be, does the function flatten off to be reaching a single value as we increase along the x-axis? The sequences is the same thing. We just have a little bit more we can do when we limit our inputs to only whole numbers. So graphically speaking, when we're talking about convergence and divergence, we are talking about the sequence approaching some number L. And some ways convergence works could look just like a function, except with only whole number inputs, where the values get closer and closer to that limit and never pass the limit. Or we could have this decrease down to reach the limit. We could also have something that moves above and below the limit, but ultimately those values get closer and closer to the limit and are eventually not going very far away from that limit either. They're getting very close and staying very close. And there's a lot of different ways we could draw out this convergence idea. Add one more that's very similar to this second one. So say we have some limit L. And another example would be we can bounce back and forth and always be above and below, but ultimately we're getting closer and closer to that limit. So the idea of converging is there is a number that the sequence terms get very close to and stay very close to. Now, some examples of divergence is that, one, we can think of divergence similar to how we thought of divergence with a function. Just it goes off to infinity. Or maybe it doesn't go off to infinity, but it never settles at one value. It just bounces back and forth between one value or between two values, three values, however many values, but never settles in on one unique single number. So there are some examples of what convergence and divergence would look like on a graph. And as has already been stated, we have our first theorem. That is, suppose we have a function where it's the same as the sequence at the sequence inputs. If the limit of the function exists, then the limit of the sequence is that same number. So for all the rules you learned back in Calc 1 for taking limits of functions, those still exist for sequences. So if you can take the limit of a sequence, or let me back up, if you can take the limit of a function, so all those rules you knew for functions, they will apply to sequences. Doesn't necessarily go the other way. There is some very specific examples for this. One example where it doesn't go the other way is the function f of x equals sine of 2 pi x. We know sine as a function looks like this, but if I only take whole numbers, a sub 1, a sub n is equal to sine of 2 pi n, where a sub 1 is sine of 2 pi, which is 0. A sub 2 is sine of 4 pi, which is 0. And because of this 2 pi, all of the sequence terms are 0. So the sequence limit exists while the function limit doesn't. So doesn't go both ways. If the sequence limit exists, the function might not. But if the function limit exists, so if the function limit exists, then the sequence limit will also exist. Then the limit of the sequence is also well. Okay. So that's our first one, is any rules we had for functions carry over to sequences. And with any rules we had for functions carrying over for sequences, we had limit laws of functions. We have these same limit laws for sequences. So the limit laws are first, that the limit as n goes to infinity of a sub n plus or minus b sub n is equal to the limit as n goes to infinity of a sub n plus or minus the limit as n goes to infinity of b sub n. Now, these rules are working when the limit as n goes to infinity of a sub n and the limit as n goes to infinity of b sub n exist and are not infinity. There are some cases where these aren't holding true when these limits do not exist. So these limit laws hold when the limits exist. So next limit law is the one that comes up on everything, is if I'm multiplying by some number, I can pull that number out and look at the limit of everything else. Very typically, we follow that up with a multiplication rule, where if I multiply two sequences together, I can multiply those limits. The fourth limit law is if multiplication works, division works. So the limit as n goes to infinity of a sub n over b sub n equals the limit of a sub n as n goes to infinity over the limit as n goes to infinity b sub n. This one has the additional requirement that the sequence terms of b sub n cannot be 0, and the limit of b sub n is not 0. Simply because we just can't divide by 0. But as long as we rule out the dividing by 0 cases, that limit law holds. And then the last limit law is if multiplication works, so does taking a power. So the limit as n goes to infinity of some sequence to a power is going to, where the power is a number. There is no function with this power in terms of there is no n in the power. Then I can pass that power to the outside, have the limit of the sequence all to the power of p. So those are the 5 limit laws. In this video, we're getting basically all the rules, and then we'll see those rules in action in the next video. So the next rule is known as the squeeze theorem. Wrong way. The squeeze theorem is saying I want to squeeze a sequence between 2 sequences I know. So if a sub n is less than or equal to b sub n, which is less than or equal to c sub n, for all n greater than or equal to some number. Doesn't have to start right away, but eventually I can say b sub n is between a sub n and c sub n for the rest of the time. And we know the limits of the sequences a sub n, and we know the limit for the sequence c sub n, and those limits are the same. So the limit of a sub n and the limit of c sub n are both L. Then this means then the limit as n goes to infinity of b sub n must also be L. This means picture-wise, showing very intuitive, very much something that makes sense. We're saying if we have some limit L and we have 3 sequences, we have the sequence a sub n, which is doing its own thing, but it comes in to be very close to this limit L. And then we also have C, which is, again, doing its own thing, but limits into the limit L. For my picture, I have these switched. A sub n is bigger than C sub n. And then I have a B sub n in between. It's always between A and C, doing something, but it's always between. Then if A sub n is going in to that limit L, and C sub n is, since B sub n is squeezed between the 2, its limit also has to be L. We'll see this in an application in the next video. And then other rules that come up for sequences is there's a specific type of sequence known as a geometric sequence. A geometric sequence is a sequence where we're multiplying by a common ratio. So we actually had this in our application in the last video. We repeatedly multiplied by 2/3. That was a geometric sequence, where the first term would be that 2/3, and then the second one, 2/3 times 2/3. Third term, 2/3 times 2/3 times 2/3. Geometric sequence is this multiplying by a common ratio repeatedly for our sequence. So we want to know, is there some common ratios when the geometric sequence converges? So breaking it down into some different places the common ratio could be, If r is bigger than 1, for example, suppose r equals 2, something bigger than 1. Then if I looked at the sequence 2 to the n, I would get the sequence 2, 4, 8, 16, 32, and so on. This is not converging into a single number. It is growing. It's growing exponentially. Next term would be 64, then 128. It's getting big very quickly. So doesn't matter what the number is that's bigger than 1. If that common ratio is bigger than 1, the geometric sequence will diverge. Now, trying if r equals 1, then we'd be looking at the sequence 1 to the n. And 1 to the first is 1, 1 squared is 1, 1 cubed is 1, 1 to the fourth is 1. Our sequence is just 1 repeatedly. The idea of limits is that eventually our sequence gets really close to a number. In this case, it started really close to a number and stays there. This sequence converges to 1 because it has gotten really close to a number, 1, and it has stayed there. If r is between 0 and 1, an example between 0 and 1 would be r equaling 1/2. Then our sequence 1/2 to the n would be the sequence 1/2, 1/4, 1/8, 1/16, 1/32, and so on. The denominators keep growing, and the bigger that denominator gets, while the numerator stays 1, these fractions are getting closer and closer to 0. So this sequence converges to 0. And we saw, again, an example like this with the application, where the bouncing ball being multiplied by 2/3 over and over would ultimately converge to 0 because eventually the bouncing ball would stop bouncing. Next ratio to consider would be if r equals 0. R equals 0, well, anytime I multiply by 0, I get 0. So 0, 0, 0, 0, just like the ones, this converges. But it converges to 0 this time. If r is between -1 and 0, our example would be r equals -1/2. What's going to happen here is we're going to have the same sequence as 1/2 to the n, but instead, the signs are going to switch back and forth. Because when n equals 1, -1 to the first is negative. And when we square a negative, we get a positive. Cubing a negative, we have a negative. And so the signs switch back and forth. The numbers are still staying the same. And since those numbers are still staying the same, and we're still getting close to 0, 0 and -0 are the same thing. So whether we're converging to 0 from above 0 or converging to 0 from below 0, that's the same. This is that example of convergence where we're bouncing back and forth above and below the limit, but we still go in to that limit. So just because the negatives are switching, we still converge to 0 here. However, r equals -1 is a different story. So looking at the sequence -1 to the n, the signs switch back and forth, but the values stay 1. So we have the sequence that's -1, 1, -1, 1, -1, 1. Limits existing is they have to get close to a single value. This is bouncing between two values, and we saw this example actually in the first video, where this is what is known as divergence, because there's not one value we're getting close to, there's two. So this diverges because there's not a single value. And then last, if r is less than -1, say r is equal to -2, it would be the same as that sequence of 2 to the n, but with the negative sign switching. -2, 4, -8, 16, -32. What's happening picture-wise is we are increasing the distance from the x-axis every time. We're getting farther and farther away. We're not getting close to a single value. So just like the r greater than 1 diverges, r less than -1 diverges. So taking this table together, this means our sequence, r to the n, converges if r is between -1 and 1, +1 included. -1 diverged, but +1 converged. Where the limit as n goes to infinity of r to the n equals 0 if the absolute value of r is less than 1. This is -1 is less than r is less than 1. And it equals 1 if r equals 1. And r to the n will diverge all other values of r. So we have a nice rule now for if we see geometric sequences. And our last sequence rule before we see examples in the next video is growth rates of sequences. And hopefully you saw this same information in section 4.7 of Calc 1, which would have been L'Hopital's type things, where the growth rates of functions can also be applied to sequences. So a few notes. We know for a fact that if the limit as n goes to infinity of a sub n over b sub n equals 0, then b sub n grows faster than a sub n. And if the limit equals infinity, then a sub n grows faster than b sub n. We use this double less than sign to say that b sub n grows faster than a sub n. And we get the theorem that we know some growth rates where natural log stuff grows really slow, then polynomial stuff grows faster. Then exponential is even faster. Factorial, and I will talk through what a factorial means, is next. And then finally, the fastest thing is this n to the n. It should be like 10 to the 10th. We multiply 10 times. So this ordering applies. And we can use this for if we see certain functions and I know some things grow faster than others, I can apply this to my sequences. And we'll see examples in the next video. The last thing I want to mention is if you haven't seen this notation of n factorial before, we will be using it in the coming sections quite a bit, but n factorial means n times all the numbers before it, all the whole numbers before it. So n times n minus 1 times n minus 2 times n minus 3, and so on. And we stop at multiplying by 1. So 5 factorial is equal to 5 times 4 times 3 times 2 times 1. And one note, we won't see it much yet, but 0 factorial, for a definition to make things work nice, 0 factorial is 1. We will see all the examples for how to use all these different sequence limit rules in the next video as we continue with this section.